Hi, Sarah.
Hi.
How are you today? So what are we going to do today?
I don't know. We had a quiz today, which means we finished our little factoring unit or whatever it was.
Okay.
So I don't know when our test is coming up, so I'm looking through the book now.
Okay.
I think the next thing we're doing is polynomial equalities and solving them. Inequalities.
Okay. Those can be challenging. Should we do
Oh,
something?
and I learned the California method, and it's actually really cool.
Oh, okay. So tell me how to do the California method on this one right here.
Okay, so the California method is for ones where you have a coefficient larger than 1 in front of the x squared. So, like, if you made it like, yeah. Okay, so then you would make two fractions, and you would take 2x and put it on top of both fractions. And then, is there a, for the last
Well, I
term?
don't know what number would make this factor or make it nice. Let's see. 3 and 2. 3 and 2. 3 times 2 would be 6. 2 times x, so maybe 4 and 6 perhaps?
Okay, so then you would take negative 6 and multiply it by 2. So then negative 12 would be your denominator. No, not negative 12, sorry. And then you would have to figure out what would multiply to negative 12 but add to negative 4.
Okay, let's see. If I did it my way, I would know that it's got to be plus minus or minus plus. And if I did 3 and 2, that works.
So I get, what do I get? 1 second. Trying to figure out what I get.
So what do you do under the denominator here?
I believe you take what multiplies, so you multiply 6 and 2,
Okay.
so it gives you negative 12, and then you find out what you can multiply to negative 12 and add to negative 4, and you use those numbers as the denominator. I'm trying to figure out how to get it. So 6 and negative 2, I think. Do that? Right? Yeah.
Well, this factors actually into plus 2 and minus 3. In other words, if I were to factor that, I would get 2x plus 2, x minus 3.
Yeah, because then when you factor it out, I don't know. We're still working on this one. But it's cool. You can get it to work.
Yeah.
I'll show you next time that one. So, inequalities.
Yeah, inequalities. What have I said this? Well, if you have some, by all means, let's look at them. But if I said that, to solve this, we need to factor it. Okay?
Okay.
Now, the solution from here isn't that obvious. It might seem obvious when you're multiplying things, but if you have a rational, in other words, if I have something like this, then the only method that's going to work is the one I'm about to show you. When I get this, I figure out what my critical points are. My critical points being whatever makes this equal to 0 or divide by 0. So what would my critical points be?
Equal to 0 is what you said, right?
Uh-huh.
So it would be positive 3 and negative 2. Yeah.
Okay, now I draw a number line. Have you heard of the concept of a line chart?
Maybe. Is it where you, like, graph it on a number line?
Right, but since these are my two critical points, and I didn't label 0 on purpose, what I want to do now is I want to check one point to the left of -2 and figure out whether it's positive or negative. And then I'm going to check a point between -2 and 3, and then I'm going to check a point to the right of 3. So let's check -3. If x is -3, am I positive or negative?
If x is -3, are you...
Yeah, so that would be negative, and that would be negative. Negative times negative would be positive, so these would all be positive. And what that tells me is that if I use an x, anything to the left of -2, I'm going to get a positive result from that.
Okay.
If I use an x in between these critical points, let's plug in 0. Well, now I have a negative times a positive, so these are all going to be negative. Now I try a point to the right of 3. So let's try 4. Well, 4 gives you a positive there, a positive there. These are all positive. So my solution to this inequality is x can be less than -2 or x can be greater than 3. That's how I solve the inequality of that quadratic.
Okay.
And it's harder if I make it a quotient. Let's just do that real quickly. Let me erase that quadratic.
You still have to, you know how when you're graphing like regular inequalities, and you have the less than or equal to, you have to fill in the dot or leave it open?
Yep.
You still do like open and close dots for these
That
ones?
one's open. That one's open because this is greater than only. It's not greater than or equal to.
Okay.
Okay? So, yeah, I would have to state this in other words, if I used interval notation, it would be -infinity to -2 combined with 3 to positive infinity would be my solution for that. You're familiar with interval notation?
Nope.
So the way you would give this answer then would be x is less than 2 or x is greater than 3.
Yeah.
All right. That's fine. Let's look at a harder problem where we have a ratio of two linear functions. Well, again, my critical points are whatever makes this 0, which is -2, or whatever makes the numerator 0, which is 3. So I have the same critical points, only now let's try -3 again. Oh, interesting. This is going to give us the same answer. In other words, when I plug in -3, I have a negative divided by a negative, which is positive, so these are all still positive. When I plug in 0, I have negatives. And when I plug in a number greater than 3, I have all positives. So this has the same solution set as the other one did. In other words, x is less than or equal to -2, or x is greater than 3. Now, if I change the sign on that, then what is my solution set?
If you change the sign on, okay.
Yeah, if I make the problem, that has to be less than 0.
Would your signs flip?
No, this is the solution set now.
Okay.
In other words, x has to be greater than -2 or less than 3.
All right.
In other words, I need this quantity to be negative. Well, the only place it's negative is between -2 and 3. It's positive everywhere to the left of that. It's positive everywhere to the right of that. So
Okay.
I'm trying to figure out what values of x satisfy this inequality. And
they're always going to be greater than or equal to 0, right?
Well, we can turn them into that. They're not always necessarily going to be that. Sometimes we will have to move something over. Yeah, you always want to get 0 on one side. It's like solving a quadratic. You can't solve it until you get 0 on one side of that inequality sign. I've got some problems in my book, I just don't know where they're at, where you start out with a polynomial on the left side and the right side, and you bring the one on the right side over to the left side, and by the time you're done manipulating, you have a quotient. You have a polynomial over a polynomial. Now, if you end up with something like this, say you get that, and we want to solve that being less than or equal to 0. So what are my critical points?
Your critical points would be positive 1, right?
Uh-huh.
Yeah. Okay. Negative 2
Uh-huh.
and positive 3.
Okay, so now I need to put in the 1 there. And now I need to solve 4 areas. I need to solve this area, this area, this area, and that area. Okay? So stick in a number to the left of -2, and let's see if this thing's positive or negative.
-3.
Okay? What's this term, positive or negative? We don't need to know the number. We just need to know the sign that it would be.
Negative.
What about this one?
Negative.
And what about this one?
Also negative.
So all 3 of those combined?
Negative. Positive.
Negative.
Negative?
In other words, this negative times that negative is positive, divided by a negative is negative. So anything to the left of -2 is negative. Let's try numbers between -2 and 3, or excuse me, between -2 and 1. 0 is the easiest one to try. What do we get when we plug in 0 for x?
Okay, you get negative, positive, negative.
Which turns into a what?
And then is it positive?
Yeah, you got a negative divided by a negative is a positive, and then positive times a positive.
Okay, I get this. This is like the 7th grade all over again. Okay.
Okay, let's finish it. So let's plug in a number between 1 and 3.
2, I guess. So that would be negative.
Hold it. That term's positive.
Yeah, sorry. Positive, negative.
So that is negative.
Negative. Okay.
And then a number greater than 3, this is always going to be positive in this problem. So our solution set to this would be what?
Less than -2 and less than 1.
Greater than 1, less than 3,
Less than 3.
and that's it. In other words, we need that area and we need that area, which is defined by that. Okay. How about problems out of your book? Because I may be getting a little off base here.
Okay. So
By off base, I'm not sure you're going to deal with that degree of difficulty where you have to use a line chart, but maybe.
yeah, there's all sorts of line charts in my book already.
Okay. Good.
It has ones that, okay, so some of them are like the ones we just did.
Okay.
And then others say things like x squared minus 4 is less than or equal to 0.
Okay, that's easy. How's that factor?
To x and -2, and then x and +2.
So that's what we solve. So our critical points are
positive 2 and negative 2.
okay. Set them up on a line chart. I leave 0 off there because I don't want to accidentally treat it as a critical point. So we would have to check a point here, a point there, and a point there to come up with our answer.
Okay, so you could do negative 3.
Okay, what do we get?
It would be a negative and a negative, so positive.
Okay.
And then you could do 0, so it would be negative. And then it would be, if you use like 3, I guess it would be positive, positive.
So your solution is what?
Your solution would be x is greater than negative 2 but less than 2.
This area right there. And if you wanted to graph that on the chart, use open, open, like that.
Okay.
Okay?
Alright.
Let's see if we can find one where we don't have 0 on one side. We're going to have to manipulate it to get 0 on one side. You have any like that? You might not have any.
Yeah, I do. Okay, this one looks annoying.
Okay.
So it says x to the power of 4
I hate it already. Go ahead.
plus 100 is greater than or equal to 29x squared.
Okay.
And it wants you to find and graph the solution for the inequality.
Okay. So we need to move our 29x squared to the left, leaving 0 on the right. Right?
Yeah.
It's a permissible step. Now, let's see. Do we have factors? Notice that even though this is a quartic, I can kind of look at it as a quadratic.
Okay.
You see why?
Yeah.
Okay. The definition of a quadratic really is that you have a term that has an exponent that's twice what this exponent is. In other words, I could say this is a quadratic. Because this is twice that.
Okay.
You can solve it as if it were a quadratic based on that. So, in other words, I know my answer is going to be x squared minus x squared minus. And I need factors of 100 that add to 29. Well, that doesn't sound easy at all. 20 and 5 add to 25.
25 times 5, but that's 45.
That doesn't add to 29. 25 and 4. We were all around it. Okay, so that has to be greater than 0. And these can each be factored. Notice each one of them is difference of perfect squares.
Yeah, which is nice.
What are they?
Negative 2 and positive 2, and negative 5 and positive 5.
So our critical points are 2, minus 2, 5, and minus 5. Okay, let's look left of minus 5.
Oh gosh. Can you put them back into the x Oh, I guess that would be annoying as well.
The easiest thing is to put them into the factored inequality.
Okay.
Because
So,
then we'll just be able to multiply negatives times negatives to come up with positives and stuff.
okay. So from left to right, it would be negative.
You know what? I'm not sure I was right there. It might actually be easier to put them back into that.
Really? Okay.
Well, I was just sitting here thinking. Yeah, because negative 6 is going to produce a positive there and a positive there.
Oh,
So it has to be positive.
yeah.
So I only have to plug it in 2 places instead of 4 places. Because if I plug it in down here, I got what? I got a negative, a negative, a negative, and a negative. It's 2 positives.
All right. Yeah.
So let's plug in up here, and it'll make it easier. So the next one we're going to try is...
So you could go like, could you use negative? No, you couldn't. Okay.
I always try the smallest number I can.
Yeah.
In other words, the easiest, the one that gives me the easiest math. How about negative 3
Okay.
as opposed to negative 4, just because it's
So
a
if
smaller
you
number.
negative 3, you would get a positive and a negative, which would give you a negative.
Correct. How about 0?
2 negatives, which would give you a positive.
And 3.
That would give you a positive on that side and a negative on the other side, so a negative altogether.
And 6.
Positive and positive.
So we need it to be greater than 0. So our solution is there, there, and there. Cool, that was a good problem. I liked it.
Okay.
I haven't done these for a long time, so it's kind of fun. You know,
Trying to find more ones
yeah.
difficult.
That one was pretty difficult because it was a quartic. It was a quadratic disguised as a quartic.
There are lots of those. There's like 3 or 4.
Good.
Oh, this one looks interesting.
Okay.
A little bit. You have to factor in things.
Mm-hmm.
So in the first set of parentheses, it says x squared plus x minus 2. End parentheses. And then it says, in another set of parentheses, x squared minus 4x plus 4 is less than or equal to 0.
Okay, this factor is fairly easy. Now, do we need to factor it? Yes, because we need to figure out our critical points. In other words, we can't start substituting values directly in here because we don't know where our critical points are on the number line. So this one factors how?
Okay. It would be positive 2 and negative 1.
Good. And this one factors how?
It would give you negative 2, negative 2.
So our critical points are negative 2, positive 1, and positive 2.
Since it's like a double factor over here on the right,
I don't think that's going to matter.
so you don't need to like do it twice. Or...
No.
No.
In other words, it's the same place on the number line. Well, we may need to, let's see what happens. We're going to have to double use that twice when we plug in numbers. So when we plug in negative 3, what do we get up here?
You get negative, 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 yeah, dumb.
So
Negative.
you do have to plug it in for both spots, and that matters because it turns the whole thing positive when you have 4 negatives together. So that's positive to the left of negative 2. How about between 2 and 1?
You would get positive, negative, negative, negative? Yeah.
Positive, negative, negative, negative. What's that equal?
Negative, negative.
And a number between 1 and 2. Let's try 1.5.
Okay. Yeah, that's not hard. Positive, positive, negative, negative. So it's
And then a number to the right of 2.
positive, positive.
They're all positive, yeah. So our solution is only there. So x has to be greater than negative 2 or less than 1. Now, could we have told that without factoring? I don't think so. In other words, if I tried starting from this to come up with this solution, I got no idea how I can do that without first factoring and then checking the points on the line chart. Because notice they don't always go plus minus either, even though every other one we had did alternate. This one went plus minus plus plus.
Okay.
Now, the really hard problems are going to be where you end up with a quotient, not a product. I guess, I'm not sure why I say that's harder. It really isn't harder. In other words, when you're dividing something by something else, when I have, x plus 1 divided by x minus 3 times x plus 2, I still go through the same process. I put plus or minuses on each of these and figure out whether it's greater than or equal to 0. So having a quotient is fundamentally the same as having a product in terms of how you solve it. You have to use the line chart. It's just that it seems like I came upon the realization once that when you have a product, you don't really need the line chart. You could figure it out without the line chart. But when you have a quotient, it's almost impossible to figure out without the line chart. So I end up doing the line chart for all of it whenever I have either. And you might have to do a common denominator sometimes, where you might not start out with a quotient, but you'll end up with one. I can't right off the top of my head think of a problem like that, but how about some more out of your book? Look for the toughest one you can see.
Okay. I have a, oh, okay, this one looks fun. X squared, and then in parentheses, x squared plus 9, and in parentheses is greater than 6x cubed.
Yeah, there we go. Looking for something like this. Now, let's notice something else right off the get-go. We cannot divide both sides by x squared. Or can we?
You could try.
Well, here's why I said that. If it was this, I could not divide both sides by x. Why? Because I don't know if x is positive or negative, and it would cause me to have to turn this inequality around. depending on whether it's positive or negative. So I can't do that. Okay, so that's not a way to solve, not the way to solve an equation either, but it's definitely not the way to solve an inequality. Now, I said, can we divide by x squared? Actually, we can. Why?
Because the exponent on the right side is greater than x squared, so you can divide by it. And
the point is, the thing is that x squared is always a positive number. So I don't have to worry that I'm going to potentially change the direction of that sign when I divide by x squared. If I divide both sides by x, definitely can't do that. But I hadn't seen a problem like this before, where you should be able to divide both sides by x squared. And the only thing that we might lose there is we might lose a solution of 0. And I can tell that that is not a solution. In other words, when x is 0, 0 is not greater than 0. So x being 0 is not a solution, so I don't even need to worry about that. So I think I could take a shortcut here, divide both sides by x squared, and end up with this. Then I can move that over, so I have x squared minus 6x plus 9 greater than 0. Does that factor into?
Okay, so it would be -3, -3, right? Yeah.
Huh?
Yeah.
So my only critical number is 3. So I merely have to test left and right of 3. So if I try 2,
negative, positive, because it's 2 negatives.
okay, and if I try 4,
It would give you positives.
so what's our solution?
All real numbers?
Yeah.
Yeah? Okay.
Huh?
Because then, yeah, because it's all positive anyway, so you can't.
Yeah, notice why that's got to be the case. Let's go back and distribute this and see what we have. X to the 4th plus 9x squared. Is that greater than 6x cubed? Well, notice that for all negative x it is, because all negative x, this is going to be negative and the left side is going to be positive. So positives are always greater than negatives, so it's certainly true for all negative x's. Is it true for all positive x's? Well, most of the time x to the 4th is going to be bigger than x to the 3rd, but fractions might make that different. In other words, x to the 4th is not always bigger than x to the 3rd. So, let's continue to solve this in the way that we know how. What would be the next step here? In other words, I want to solve it both methods. I want to solve it the method where I divided both sides by x squared, and now I want to solve it by moving everything over to one side and making 0 on the other.
Okay, so did you subtract 6x cubed?
Now I can definitely... Go ahead.
Should you pull out an x squared? Cause it's
That's the next step. Notice we're going to end up with something very similar to what we had. And finally, that's x squared times x minus 3 times x minus 3. It does give us another critical number, oddly enough. What are our critical numbers now?
+3 and +3.
And
Do you have
0.
to include x squared?
We have to allow for that to be 0. So 0 becomes a critical number now.
Okay.
Okay? So we've already determined that that's positive and that's positive. You know, any time I have a number a positive number these are going to have the same signs, and this is going to have the positive sign. So any positive number clearly is positive, but we need to examine negatives. So negative 1 gives us positive, negative, negative, still positive. So even though we came up with a second critical point, it didn't matter. Our answer is still all reals. So actually that shortcut I did was a legitimate, acceptable shortcut. But only because I was able to divide by x squared. Like I said, had that been an x and that been an x squared, I could not have done that. I would not have been able to divide both sides by x.
If you wanted to divide by x to the power of 4, could you also?
Yes, because that's always positive also, yes.
So like even exponents?
Uh-huh. Any even exponents you could do that. Although, let's just go over something. It's interesting to note this because I actually went through all the way through college without really realizing this. Solve that?
I don't know. You could divide both sides by an x.
Okay, so I get x equals 6.
Yeah.
Is that my only solution?
Negative 6.
No. Negative 6 doesn't work because negative 6 squared would be 36.
Yeah.
On this side we'd have negative 36. But there is another solution. But we lost it. And we lost it because you divided both sides by x, and x has the ability to be 0.
Yeah.
And so that when you divide by a variable that can be 0, if 0 is a solution, you will lose it. Just as we did here. 0 is obviously a solution because 0 squared is equal to 6 times 0. But notice it's nowhere to be found if we do what you did. So the proper way to solve this is not to divide both sides by x, but to subtract 6x from both sides. Now factor that. And notice now we have both solutions. We have x equals 0 or x equals 6. Okay? That'll be more important to you when you get into trig, where if you're dealing with trig functions, this really makes a difference because solutions that are 0 are very important solutions. Not that they're not here either. They're also important solutions to a polynomial. In other words, there were 2 solutions to this, not just one, and they were 0 and 6. But we would have lost one of them if we divided by. So you got to be careful dividing both sides of an equation by a variable that can be 0.
Okay.
And definitely in inequality, you got to be very careful about dividing by variables. You pretty much can always, in fact, I had a rule that never divide in inequality by a variable. It was only today that I realized you could actually divide by a variable squared or to an even power, an even exponent. That's okay, because you know that's always positive.
Okay. So only the even exponents.
Yeah. The safer way to solve it probably is just to subtract from both sides. In other words, make one side 0, like we did the second method there.
All right. So is there anything you could use can you still have word problems that you would use the inequalities for?
Sure.
Or are they just...
You might have a function that has to be greater than 0 for some reason. In which case you would write the function, you would say f of x has to be greater than 0. And then f of x might be x squared minus x minus 6, And now you have to factor that up into x minus 3 times x plus 2 and go through the sign chart to solve for it. But I can't think of a word problem right off the get-go that would result in a function and an inequality. I'm sure that there's plenty.
I don't have any word problems in my book, which is why I was asking. Cause
Yeah. I don't know. It's very difficult to think up a word problem that involves a quadratic or even a linear. Well, linears are easily. I mean, if I have x minus 3 is greater than 0, there's no problem. The only time they're hard is when they get to be quadratics or more. None of them are hard if you can turn it into a product or a quotient. Here's one that may, okay, I can give you another one. Let me think for a second. 1 over x plus 1 over x minus 1. Solve that.
Oh, okay. So you would have to divide?
No, remember we don't want to be dividing by much.
Subtract.
We don't even want to be multiplying by much because we don't want to multiply or divide by any combination of this variable because it might be negative, in which case we'd have to turn that around and we wouldn't know. So it's rare that you want to divide or multiply by variables when you have inequalities. So yeah, let's subtract. Let's bring that term over to the other side. And now we need to turn it into a single rational quotient. How do I do that?
I don't know.
Common denominator?
X and 1.
The product will always give you a common denominator. In other words, if I'm adding 1/4 and 1/3, I know that 12 is always a common denominator. It may not be the lowest common denominator, but I'm not so concerned when I'm dealing with variables. So when I have a variable as a denominator and I'm looking for the common denominator, just multiply them together. And then what goes up there and what goes right here.
So...
In other words, what I really have here, let me rewrite this. So I have something going to be over x times x minus 1. Then I'm going to subtract another fraction that's going to be over x times x minus 1. So what goes here?
A 1? Or... Cause,
okay, here's what we started with.
Yeah.
In order to get this denominator, I got to multiply this fraction by x minus 1 over x minus 1.
Oh, okay, I get what you're doing now.
So that leaves x minus 1 right there.
Yeah.
Now, you see how this fraction is the same as this fraction?
Yeah, I get that.
Okay. And so what goes here?
The same thing, right?
What did we have to multiply this by?
Oh, you multiplied that by an x, so now you have x. Okay.
Okay.
Okay, got this.
All right. So now we got that, and then I can remove the denominators, right?
Mm-hmm.
In other words, because I have the same common denominator, I can operate on the numerators, and I end up with minus 1 over x times x minus 1 has to be greater than 0. See how I got the minus 1?
Yeah.
X minus 1 minus x?
Yeah, because you subtracted the x's.
Right. So now let's come up. Now we have a single rational quotient. Now we can use critical points and figure out what values of x make this thing greater than 0? What are my critical points?
-1,
Not
0.
negative. 0 for this one.
1. Yeah.
And 1.
1.
Just those. So, let's look at a negative number. What's a negative number going to do here?
You don't have to include the coefficient x, right? You just...
No, I do. In other words, I want to analyze these things based on that.
So you would substitute in the same number for the x as well as the x outside the parentheses?
Right. In other words, let's try not -1.
So you'd have a -1 times a -2.
I'd have a negative there.
Would be
I have
positive?
a negative there, and I have a negative in the numerator already.
So it would be negative.
Be negative. How about between 0 and 1?
So
Positive there.
Positive in the middle, negative in the middle.
Negative. 1/2 minus 1 would still be negative.
And then, so it would be positive overall because it's 2 negatives?
Uh-huh. And then to the right of 1, plus in the bottom.
And then a negative, so negative. Yeah.
So our answer is x has to be between 0 and 1. Greater than 0 and less than 1.
Okay.
I like that problem. That was a good one. Oh, I made that up. I was thinking you gave me that. I made that up. That's the kind I was looking for, where you had to find a common denominator. You had to move this entire fraction to the other side, find a common denominator so you could put it into a single quotient. In other words, when I had it like this, I had the difference of 2 quotients. I can't work with that. So I can only do my sign chart analysis when I get it into a single quotient, like this. That's a single numerator and a single denominator.
Okay.
All right. So you haven't had any of this stuff? Is this stuff coming up in your class, or is this stuff you've partially covered? Or
this is coming up. This is what's next in the chapter.
You haven't had any of it at all?
Nope.
Fantastic. It's good that we're able to stay ahead, because this surely has to help, I would think. I mean, when it comes time to have the class on this, you're going to be able to comprehend what's being said in class so much easier, I would think.
Yeah, because then it turns into a review rather than like learning.
Yeah.
Plus, apparently we have a test coming up on this soon.
Okay. Well, I think you'll do good on it.
Okay. There's a bunch of chapter review problems.
You might not have anything like 1 over x minus 1 over x minus 1. That, you may not see anything that difficult.
Yeah, there weren't problems like that in the book, but
No, I wouldn't.
I would not put it past my teacher to do something like
Well,
that.
now you know how to do it. Just know you have to end up with a single quotient. You can't end up with 1 over a minus 1 over b being greater than 0. Have to turn that into ab underneath, and this would be b minus a. So I would end up with this. Now I can figure out my critical numbers and analyze.
Okay. You couldn't solve a problem like this with just variables, right? Like if you just, because you need like numbers to substitute in on the number line, right?
Well, there's probably other ways to do it. That's just the only one I know of.
Yeah, that's the one in the book. So.
Yeah, in other words, how would you go about solving this? Notice that if I try multiplying both sides by x minus 1, I have that risk that if x minus 1 is negative, so can I really say this? I can't. In other words, if this is greater than 0, does not mean that x plus 1 is greater than 0. I can't multiply bottom or both sides by x minus 1 to get this second line. Notice that x plus 1 doesn't have to be greater than 0. If that's negative and that's negative, the whole equation is valid. So x minus 1 can really be plus or minus. We just don't know what number ranges it can be plus or minus.
There's no specifics, okay.
Yeah, so I don't know how to make further progress on this without a sign chart.
Wait.
You know, if it was just a number in the bottom, now it's a piece of cake. Because I can multiply both sides by minus 1. So now I can say, okay, x plus 1 has to be... notice that if I multiply both sides by minus 1, it turns that thing around. So now it would say that, and that's true. X would have to be less than minus 1 if I was solving this. In other words, I can do it algebraically. I don't need a sign chart. And the reason I can do it algebraically is because I can multiply both sides by minus 1. I know exactly what it does to the inequality sign if I multiply both sides by minus 1.
Oh, it's all like math. Okay. So is that? Then should we do one more problem?
Yeah.
Okay, so this is not related to the inequalities.
Okay.
But we're doing them in class, so I figured it would make sense to do.
Yeah. No, certainly
so,
anything that you've covered that you have any questions about, let's go over it, clarify it.
Yeah, just some review. So a farmer plans to use 25 meters of fencing to enclose a rectangular pen that has an area of 63 meters squared. Okay. Only 3 sides of the pen need fencing because part of an existing wall will be used for one of the longer sides.
So this is on a house.
Yeah, I guess.
So the only thing we need are fencing for that, that, and that.
Yeah.
Okay?
And then find the dimensions of the pen.
That produce the maximum
Of
we don't even need that. We have the area.
Mm-hmm.
Okay, well, let's call this y. Let's call that x. That's y. So what's my perimeter equal to?
It's y plus y plus y. Y plus y plus x plus x.
So there's one equation. Because I know I have 25 feet of fencing.
Okay, and then you
What's
would
the second equation? Based on the area that we're given.
xy is equal to 63.
We now have 2 equations and 2 unknowns we can solve. Okay? Let's solve that.
So you could subtract the 2y.
Okay, so that makes this x equal 25 minus 2y. Now we're going to do what? Substitution?
Yeah.
So 25 minus 2y times y equals 63. So that's 25y minus 2y squared equals 63, but it's a quadratic, so I know I want to solve it this way, right?
Yeah.
In other words, I know I'm going to have to put everything on one side. Now I have a negative coefficient. I don't like that, so let's divide everything by minus 1 and put things in order. So we have 2y squared minus 25y plus 63 equals 0. Now here would probably be a perfect place for your California method.
Okay, so you would do...
I know that much. I know it's 2y, y, and negative, negative. Well, factors of 63, there's not very many of those. What's the most likely one we're dealing with?
7 and 9.
7 and 9. So let's just try 7 and 9 in some combination here. It's either 7 and 9 or 9 and 7. So let's try 7 and 9. Does that work?
No, yes.
Yes, it does. 9 and 7 would not have worked, but 7 and 9 work.
Yeah, because you don't need like 9y because 7.
Right.
Okay.
So what's your solutions? Y equals what?
Y is equal to positive 7 and positive 9, except for then...
No. Remember, this is equal to 0 or this is equal to 0. So y equal positive 9 is one solution. But when I set 2y minus 7 equal to 0, solve that.
You get 7 divided by 2.
Yeah. So here's your two solutions over here. 7 halves and 9.
And then, so could you say, and then since once you define the dimensions,
Yeah, sorry.
10, what would you,
Well, let's
do you
see.
double?
I erased my thing. So this was y. What? No, that was x. This was y. So we've come up with two solutions. 7 halves or 9 for y. Well, so what are the two solutions for x? Remember, x times y had to equal 63.
So you could have 7 and 9.
7. But 7 halves times what would equal 63? It would be 126 divided by 7, which is 18. So, or 18. In other words, there are two different possible solutions here. We can have x equal 7 and y equal 9, or we can have x equal 18 and y equal 7 halves. Notice that both of them give us a perimeter of 25 and an area of 63.
Okay.
I think, let's see, if I multiply that out, I get 63, I get 63 there. If I do the perimeter, I get 2 y's, that's 25. 2 y's here are 7 plus 18, 25. That's interesting. I hadn't seen a problem like that had two possible solutions. In other words, there's two different ways somebody could build that corral. Depends on whether you got a house. In other words, if your house is like this, you could build the corral like this, or you could build it like that, giving you the same area for the same amount of fencing material.
Okay. Someday I'm going to have to build a garden or something, and I'm just...
Well, that problem you just gave me is actually a classic calculus problem. Only it's worded, yeah, it's worded as what shape of rectangle will give you the maximum area. In other words, if you've got horses you want to put in that corral and you got only 25 feet of fencing, you want to build a corral that's as big as you can possibly build. And that's not clear. Which one, what's the maximum area you could make that corral out of 25 feet of fencing? And that is a calculus problem. Yeah. And it'll tell you the exact area. All right. Well, that was we covered a lot of stuff today. Felt like we did 2 sessions. Sarah, you still there? I lost you somehow, right at the end of the session. Okay.